Okay, recording is in process. Right. So today we are going to talk or to make a switch to a more theoretical point of view. And first of all, let me switch to our collection of slides and go to full screen mode. Can you see the screen? Wait.
Not yet.
Let me try this again. Moment. Okay, now you should see my screen.
Yeah, we see it now.
Perfect, thank you. Okay, switch to full screen mode and it should be still visible. Okay, so today we will be talking about theoretical molecular physics. So we will be entering a new perspective. I think I showed you this slide already. It's about the spectrum of electromagnetic radiation, and we were talking a bit about the possible internal degrees of freedom where we can deposit energy in a molecule or in a molecular system. We said we have electronic excitations, we have vibrational excitations, and we have rotation as a possible degree of freedom which can be excited. Typically, when we think about an excitation, it would be through photons, for example, that hit our molecular system and give rise to some excitation. But obviously, any kind of energy, if it's heat, so if you have a disordered kind of motion of particles and the particles are colliding with each other, this also triggers some sort of excitation of any kind, depending on the energy that is available at a given temperature. So that's our situation. And today we will start talking about the electronic excitation, which is the one that takes the most energy. It's a reconfiguration of the electron distribution of our system. And it is in an energy regime in the visible, so several EVs in terms of energy in the visible or in the UV range. We remember for vibrational excitations, we are in the infrared, in an energy regime slightly under the visible, so with a few thousand wave numbers typically as energies for excitations of vibrational modes. And then if we go to rotational excitations, we're in the range of several, or say around 100 wave numbers or centimeters to the -1, which is a typical unit used to refer to energies in spectroscopy. Okay, let me switch to this more abstract view of energies in a system. We said we distinguish between in terms of nomenclature as it's used in spectroscopy. We would say we distinguish between the actual electronic excitation that can happen in a molecule, which gives you a band structure, and then we have these bands which are referred to energy transformations with respect to changes in the vibrational quantum number. And each of these bands has fine lines which then refer to changes in the rotational quantum number, right? So this is how we can think of the actual discrete spectrum generated by a given molecule with a certain electronic structure, but also with certain possibilities of how this molecule can vibrate, and with respect to its moment of inertia around these three axes in space that define the actual energy distances between different states of rotation. So this is shown here. In green would be an excitation that goes from one group of or from one electronic state to a different electronic state, also changing vibration and rotation. then the blue line would be a change in vibration and rotation, and this red transition here would just be a rotational transition. So that's how we can classify them. And today, when talking about the electronic excitation, we will introduce a couple of simplifications in how we handle this on the paper if we work our way through the quantum mechanics part of this problem. We are going to switch to a system called the atomic units. So we switch from the SI to atomic units, which is a pretty straightforward and simple way of getting rid of all the numbers that in principle or natural constants which appear in our equations. We just set all these constants, such as the electron mass or the Planck constant, they all set to 1 for the convenience of having a set of formula that are for us easy to read, and we don't have to worry also when putting this into the computer. We don't have to worry about these issues of accuracy and the constants and whatnot. We can convert this to the SI whenever we need, right? The only consequence of introducing this simplifications is that we get slightly weird units for the standard units, such as energy, length, and so on. I have pointed out two physical quantities which are most relevant to us, which will be the length, and in atomic units, the length is in units of Bohr, typically written as a knot, as one piece of the Bohr length, and the energy is comes in the unit of Hartree. A Hartree is a pretty big energy unit, and you can remember, so the ionization energy for the hydrogen molecule is 13.6 eV. This is half of a Hartree. By definition, is half a Hartree. So 27.2 eV is one Hartree. And since we will be dealing with small fractions of Hartree when it comes to the transitions that we are addressing in molecules, you'll see that Hartree is a unit that makes sense for computation because of this simplification with respect to all the natural constants. But when referring to actual energy differences, when talking about spectroscopy or chemistry, different units are introduced. So spectroscopists would talk about wave numbers, so centimeters to the -1 typically, or for higher energies, and depending on the field, probably address these energies in electron volt. A very old unit would be Kaiser in spectroscopy, but you don't have to worry about this one. So it's mostly centimeters to the -1 nowadays. And but chemists would refer to energies typically in kcal per mole. Right, so this is another unit that is commonly used in scientific papers when referring to energy differences of molecular systems with respect to some kind of chemical interaction. So that's about units and the unit system. So we are now in this atomic unit system. You can see in the formula on the slide 82 how our fundamental Schrödinger equation, the stationary Schrödinger equation for a single electron in the Coulomb field looks like. After having made this transition, you can see h bar, the mass of the electron charge, and all these constants going to a set to 1. And later on, we will use this to have simple expressions in our formula as well. But before really entering the problem of the electronic structure, we have to think about the problem of a coupled motion that exists between electrons in a molecular system and the nuclei that themselves have some kinetic energy. They will be vibrating. There will be some constant change of the actual geometry of the molecule. If you think of a diatomic molecule, that means that the bond length between the two atoms might change over time, and this will obviously affect the electronic situation as well. So these two areas of motion or degrees of freedom with respect to motion are coupled. But we can assume, and I guess this is how you might have heard about the Born-Oppenheimer approach before, you can assume that these movements are taking place on a different time scale due to the significant difference in mass between electrons and the nuclei. So it is typically fair to say that the arrangement of the electron hull is instantaneous comparison to changes of nuclear positions. So at the moment I'm changing the nuclear position, the electrons will react immediately and will form a slightly different electron distribution practically instantaneously. Now, there are situations, and we will talk about this in a more mathematically and more precise way in the next few minutes, where this approximation does no longer hold. And in order to work with this concept, we have to know when it is valid and when we have to go beyond this Born-Oppenheimer approach and think a bit more out of the box. So the mathematical treatment that I'm introducing right now goes as follows. We start by writing down the wave function for the total system. So the wave function depending on electronic and nuclear coordinates. You can see this psi in uppercase, which denotes the total wave function of our molecular system. And if I'm using lowercase for r, then I'm referring to electron coordinates, and uppercase r to the nuclear coordinates. Now, we know, and you have been dealing with this in quantum mechanics and in the atomic physics lectures before, we have to solve the Schrödinger equation for this system, where we have an Hamiltonian multiplied by, or acting as an operator on psi, giving us psi times E, with E denoting the corresponding eigenvalue, and the eigenvalue of the Hamiltonian is the energy. Now, how does our Hamiltonian look like in this case? And you can see it consists of three parts, as it's written here on this slide: the kinetic energy of the electrons, the kinetic energy of the nuclei. You might realize that I've copied this from a German book, K for Kerne, TK, and we have a coupling potential, which will consist of Coulomb interactions between the charged particles, which is obviously a function of electronic as well as nuclear coordinates. We switch to the next slide, and here we do now the following. Look at the first equation, which is marked. You can see this is only the electronic part of the wave function. So we do the following. We look at the electronic situation. Electrons in this, electrons described as a electronic wave function. So the total electronic wave function here denoted as phi m. Okay. You can see it's written as a function which depends on r and uppercase R. Why? Because depending on how your molecule is shaped at the moment, so depending on the nuclear positions, you will end up with a different solution for the electronic wave function, right? So this is the problem to be solved. for a given nuclear position. And since this Schrödinger equation that we are solving here for the electrons is solving the problem for different core positions at the same time, we don't get just a single eigenvalue, but the eigenvalue that we generate will be also dependent on the geometry of this molecule, right? So this is why we have the corresponding eigenvalue that corresponds to this electronic state. We denote it as phi m. This eigenvalue that corresponds to this electronic state is a function of r, of uppercase R. In other words, we are generating something like a potential because the energy, the electronic energy of the system is a function of the coordinate arrangement of the molecular system. Okay? So this equation is just a rewritten h times phi equals E times phi. Our energy E is in this case denoted as W. This is this is the eigenvalue, and the eigenfunction is our electronic state. To extend the perspective a little bit, there will be many electronic states that fulfill the differential equation given by this Schrödinger equation here for the system. So there is not just a single electronic state, but a whole bunch of electronic states. We can say there is a ground state. This is the one with the lowest energy. And then there are many excited states. And all of them are possible arrangements for electrons in this molecular system. And now comes the trick, okay, that helps us to deal with the Born-Oppenheimer approach in a more general and more accurate way. We're doing the following. We say that the actual total wave function of our molecular system, and when I say total wave function, I mean a wave function that describes electrons and nuclei at the same time. This wave function can be expressed through our electronic states that we had before. Okay, so let's assume we were able to solve the electronic part of the Schrödinger equation and get all these eigenenergies, which are potential curves, and the corresponding electronic wave functions. And if we have now all these solutions, we know all the electronic wave functions that work for this situation here, we can use them as a basis and describe any type of wave function depending now on electron and nuclear coordinates as a linear combination of these basis functions. The only thing that we have to keep in mind is that if we want to have this function also to be dependent on R and our linear combination to be flexible enough to describe any type of function which depends on electron and nuclear coordinates, we will have to introduce coefficients, which are written as chi here, chi m, coefficients which themselves depend on the nuclear coordinates. Okay, what does this mean? This means that depending on the actual nuclear arrangement of your molecular system, you will have a different type of mixing of the possible electronic states that form the actual state of your molecular system. Okay, so this is the idea. We take our set of basis functions. We can, for example, say we solve this at a given position in space. So in saying that we are looking at all electronic excitations for a given geometry and use this basis now, all these electronic states, to describe any total wave function of our molecular system in this basis. But in order to also take into consideration that at different positions or different shapes of the actual molecule, different electronic states of this basis set will get more or less important, our coefficients in this linear combination must be dependent on R themselves. Okay, so then without losing generality, we can describe any wave function uppercase psi as this linear combination. And we can use this ansatz and go straight into our Schrödinger equation for the total system, now with our expression for the total wave function expressed as this linear combination in our basis. This is happening here in this line. We can write it as, and now here come all the operators that define the total Hamiltonian of our Schrödinger equation. And the corresponding eigenvalue that we are seeking is denoted as E. Okay, so far we haven't lost any accuracy. We have just made this transformation. We rewrote our total wave function psi as this linear combination. And now what we're doing is we are multiplying this Schrödinger equation from the left with an arbitrary electronic wave function from our set. It's coming from the left, therefore it's denoted as phi star, and it's some arbitrary wave function from our set. I give it the index n and multiply it now from the left onto our equation. Okay, so that's what leads us to this equation here at the bottom.
I have a question about this. Can I ask a question?
Sure.
The line before, why did you include again the kinetic energy of the nuclei? Because it says Te plus Tk, but then I wonder, because this is actually a derivative with respect to big R, but if I apply this to the function on the right-hand side, I would differentiate my coefficients and my phi's. Does this really yield the kinetic energy of the nuclei? Or why are they there in the first place? Because I thought we were just considering electrons.
Yeah, okay. So let me explain this again. So at first, this the question, the equation marked with this diamond symbol here. This is the electronic Schrödinger equation, and we assume that this equation is solved, because if it's solved, we know this set of electronic eigenfunctions, and we know for each electronic eigenfunction its corresponding eigenenergy, which we said is a potential kind of surface. It's an energy as a function of the nuclear coordinates. And so this is where we start with, and with this we go now back into the main and actual Schrödinger equation for the total system, not just for the electronic system, but for the total system. So we look at the Schrödinger equation for the system of electrons and nuclei. Therefore, the Hamiltonian in this line here is the Hamiltonian of the total system. We just used this preliminary work here to be able to replace the total wave function by this linear combination where we have a product of an electronic wave function times a coefficient which only depends on the nuclear coordinates. So I'm now really switching back to the actual total Hamiltonian of the system. Okay, so this is why the kinetic or the full range of all the operators we need to have the Hamiltonian build is occurring here. Again, the kinetic energy of the electrons, but now also the kinetic energy of the nuclei, right? So we're basically solving this problem for the total system consisting of electrons and nuclei. And you are right, this will introduce now some issues because the kinetic energy operators are second derivatives with respect to the coordinates of the particles we are talking about. So it's electrons or a nuclei. And this means that the operator here, when acting on our sum here, will do quite something. And this is something I'm going to show you on the next slide. So for now, we have just translated the total wave function we expanded the total wave function in this series. We go back into our formula, which is the Schrödinger equation for the total system of electrons and nuclei, and multiply from the left with an arbitrary electronic state now, okay, with some electronic wave function phi n. And we take now advantage of our solution, which we obtained for the electronic part of the Schrödinger equation. We said that on the previous slide, I said we have already solved the electronic problem of the Schrödinger equation for fixed geometry. And the corresponding energy eigenvalue, which describes the electronic energy, is this term we denoted as W. Wm of R is the corresponding eigenstate for the electronic state phi m. Note that it's not just a scalar value, but it is a potential surface because it's still dependent on the actual nuclear coordinates, right? Okay, so see what I have done. I have taken, let me go back. I have taken this equation where I see that kinetic energy plus this potential term acting on phi m gives me the corresponding eigenvalue Wm of R. So I have replaced Te and Tv by this eigenvalue Wm of R. Okay, so I have used my knowledge which I have from the solution of the electronic Schrödinger equation. But this equation that I'm working here right now is the Schrödinger equation for the total system. Now I'm taking advantage of the orthogonality of the electronic states, which tells me that if I'm doing a spatial integration of a product of my electronic wave functions n and m, then this gives me either 0 if n and m are different, or 1 if it's the same wave function due to the normalization that we request. Okay, so with this knowledge I can simplify because, okay, T is an operator, here I can't do much, but this is just a function of R, and this is a constant. So I can pull my phi of n, which is coming from the left, over and execute the integration, which gives me a delta nm here. So you can see the energy E, so this eigenvalue of the total energy, also of the actual total Hamiltonian for the system, is here in this delta m, and the other term that has this or gives this delta is this Wm of R. Okay, so far so good. Now we have to think about or worry about the kinetic energy operator for the nuclei. And as you said already, it is a second derivative, but we see that it's not just that phi of m is a function of R, also this coefficient chi m of R is a function of R. And therefore, when the operator is acting on this product, we have to stick to the product rule, which is something I repeated here for you just to make it easier to kind of read through the slides. So we take the first derivative ending up in these two terms, and then we take the second derivative, which leads to these terms. Note what's going on. We have a second derivative of the electronic wave function with respect to the nuclear coordinates times our chi m. Then we have a mixed term, which is derivatives of our phi and of our chi. And finally, a term where we only have a second derivative of our coefficient chi multiplied by the electronic wave function of the mth state. Okay, so this is what the second derivative produces. And with this knowledge, we go now back into our formula. What's written there is the kinetic operator acting on this product, as we just looked at, and then multiplied from the left with our electronic state phi n. Now, since in these three terms, the last one, I go back one slide quickly, I go back one slide. The last in our second derivative, the last term is only acting on chi and leaves phi of m as it is. So if we multiply now from the left with phi of n star, we can use orthogonality, and this means that the last term of this integration has this delta nm. because phi n from left meets phi m from the right, giving us this delta nm. Okay, so these are the three terms that stem from the second derivative: a first term, a second term, and the third term. The first term has the second derivative of the electronic wave function. The second term has these mixed derivatives, one of the electronic function and one of this coefficient. And the third one has the second derivative only for the coefficient and the delta nm because of the orthonormality. Okay, we're almost through. So what am I doing now is now we're putting everything together. And what I do is I'm taking this delta nm term on the right-hand side and put it to my other delta nm terms in this total Schrödinger equation and have them all on the left-hand side of my equation. And the remaining parts of the kinetic energy operator I put on the right-hand side. So this leads to this equation here, see? We have put all the delta nm's on the left-hand side, and we see that because of the summation over the m states, this will only cut out the state where n equals m. So on the left-hand side, we have this expression. We have our, let's start here. We have our energy eigenvalue that we're interested in. We have what's left when we solve the electronic Schrödinger equation, this term W of R, which corresponds to the electronic energy as a function of the nuclear coordinates. And we have this one term of the kinetic energy operator for the nuclei that did not include the derivative of the electronic wave function. Right? I put it all on the left-hand side, and what's left on the right-hand side are these two other components of our kinetic energy operator. The one that has the mixed derivatives and the other one that has the second derivative of our electronic wave function with respect to the nuclear positions. And now we are almost at the end. Okay, so now we do just a formal simplification. And then we do a big thing. A large part will be simply set to 0. So what are we doing now? We say that this expression on the right-hand side, this is something we define as a coupling coefficient lambda nm. So lambda nm is basically what's left from this second derivative that we had through the kinetic energy operator for the nuclei. Delta nm, and so we still have the sum over m outside, so we end up with this equation in the end. This is our Schrödinger equation for the total system, where we have introduced an abbreviation for the two terms of the kinetic energy operator of the nuclei with these derivatives of that contain derivatives of the electronic wave function with respect to the nuclear positions. Okay, this is in this lambda here, and so it almost looks like a nice equation here. I mean, it's everything, the derivatives are hidden here. Here are the kinetic energy of operator for the nuclei. This is our term, which we said is something like a potential energy. It is the eigenenergy of the electronic wave function. And we said this is also a function of the nuclear positions in space, so therefore it is still dependent on R. And E is the eigenvalue we are looking for. And now comes the Born-Oppenheimer approach, which is simply assuming that all these coupling terms on the right-hand side are 0. Okay? It says that there is no real coupling with respect to second derivatives of the wave functions of electrons and nuclei, or they're small enough to be neglected. And in this case, we are left with a pretty simple differential equation, a simple, much simpler Schrödinger equation which can be solved now for this chi, these coefficients that we introduced. And so what we now realize is that this Kn is something we can interpret as the actual nuclear wave function that describes the motion of the nuclei. Because what do we have? We have a Schrödinger equation where we have an operator which contains the kinetic energy operator with respect to nucleus, atoms, so the nuclei, in a given potential Wn of r. What is this potential? This is simply the electronic energy as a function of the nuclear positions. So you can think of it the following way, and unfortunately, because of an update on my Mac, my computer does not talk at the moment to my iPad, so I have to do it in a classic way and show you this here on paper, okay? So I'll do some drawings now for you. First of all, I look at the system where everything is much clearer, namely the diatomic molecule, because for a diatomic, we only have 1 degree of freedom in the geometry, because the only thing we can change is the distance between the 2 atoms, okay? So we are solving now the electronic Schrödinger equation for different positions in space. And as you will hear in this lecture and in the next lecture, this is the actual tricky part, to solve the electronic problem. But let's assume we can have a cool algorithm which solves our problems for the electrons and gives us electronic energies as a function of distance. Now I do a scan. I scan over energy as a function of the distance between my 2 atoms. So wait a second now to make this a bit more visible for you. I stop sharing. Wait a second. Stop sharing. Yeah. So because then you can see better what I'm about to show you. Okay, we look at the diatomic energy, the energy as a function of the distance, the electronic energy as a function of the distance between 2 atoms. And if I plot energy as a function of distance written as r, I typically get for the lowest electronic state something that looks like this. Okay, this is our potential energy surface, which in the case of a diatomic molecule is a pretty simple surface. It's actually a curve, right? Energy as a function of just 1 coordinate, the internuclear distance. This is what we get. Okay, so this is our potential energy surface, as we call it, and depending on the actual electronic state that we are looking at, this potential energy surface will look differently. Let me illustrate this in the same drawing. Let's assume this is the ground state, okay? And now I'm exciting the molecule into some electronically excited state. And I look at the energy, electronic energy of this excited molecule as a function of the nuclear coordinates, so as a function of the internuclear distance in our diatomic molecule. It's going to look like this. For example, okay, we have a second potential energy surface. And our solution we came up with now when introducing the Born-Oppenheimer approximation, and now I have to share again. This might introduce some problems with the recording, so it's good for you that you are here with me right now. I hope those who are not can also profit from this or benefit from this lecture. So, okay, you should see my screen again. And so look at this equation here. This is a Schrödinger equation which remained for these coefficients that we introduced, chi, n, and they are now also dependent on some other quantum number, which I've denoted as nu here, because I can find several possible eigenfunctions for this situation where we have our nuclei in a given potential. Now the potential term, the thing that I was just drawing on the paper, is dependent on my actual electron situation, right? It's a different electronic state that gives a different potential energy surface. And you can think of the remaining part, this Schrödinger equation that's left here, which is the Schrödinger equation for the nuclear motion, as a simple, in our case, with the diatomic molecule, as a simple one-dimensional Schrödinger equation problem. You have a dimension, you have a potential energy surface in one dimension, so a one-dimensional potential, and you're looking for solutions in this potential, right? So you're just solving a one-dimensional Schrödinger equation. You have a certain potential and you have a certain mass, which is then the reduced mass of your diatomic system. And this mass is somehow oscillating in this potential. This is your vibrational motion. And we realize that the coefficient that we introduced, this coefficient chi, is my actual nuclear wave function. Okay? Because look at the remaining equation here for our Schrödinger equation for the nuclei. It's exactly that. You have a kinetic energy operator for the nuclei. These nuclei are sitting in some sort of effective potential, which is generated by the fact that for each different position, your electron energy will be a little different, right? So this is like a potential that the nuclei can feel. Because if you pull them apart, electrons won't be too happy, electron energy will go up. So this introduces something like a potential that our nuclei feel while vibrating, basically, okay? So our chi is the nuclear wave function and is the result of solving the nuclear Schrödinger equation in the potential created by the presence of the electrons. Because when you change nuclear positions, your electronic state has to rearrange. The electronic energy will be slightly different. Okay, and this gives rise to this potential that is holding in the ground state, is holding our nuclear system together. Because you can see, typically, in a bound state, there is a certain geometry, so a certain distance between the two nuclei, at which the energy is minimal, which is the most convenient distance between the two atoms. This means that for different electronic states, you will have slightly different equilibrium distances, right? Because in some electronic state, a distance of 1.2 angstrom would be the perfect, would be lowest in energy, but for some excited state, it might be different. Okay, so what have we learned here? What is it that we realize? We realize that the idea of a potential energy surface does only make sense within the Born-Oppenheimer approach, where we have set these coupling coefficients to 0, because in this case we are left with this simple equation, which is which can be solved easily. Differential equation for the kinetic for the nuclear wave function in the potential, which is a consequence of the electronic energy which changes with distance. Okay? I'm saying that this is only possible within the Born-Oppenheimer approach because we have neglected these coupling terms, and an actual change of the nuclear position will trigger a direct answer of your electron energy, of your electron distribution. And the derivatives of the wave function of the electrons with respect to the nuclear positions plays a role for the energy. But if we say, okay, this can be neglected and the coupling is very small, then we are in this Born-Oppenheimer approach where each electronic state gives a potential energy surface, and we can look at the molecular ways of how a molecule can vibrate by simply sticking to one electronic state and looking and solving the problem for this potential energy surface, which is just effective mass moving in this potential which stems from the electron energy. So, is this somewhat clear?
Can I ask a question about it? Actually, two, I think. One, the total wave function is now composed of the product of the two wave functions.
Exactly.
And it should account for both the presence of nuclei and the presence of electrons. What I was wondering is, I would think that the probability for electrons to be located where the nuclei are located is zero, and the probability that nuclei are located where electrons are located is also zero.
Yes.
So I would think that if I multiply the two together, then if I evaluate that function at the position of a nuclei, the nucleus, I should get zero because of the electron contribution. And if I evaluate it where an electron is, that's more a cloud, but then that would be zero because the nucleus gives zero. Do you know what I mean? So I'm wondering, if you multiply it, why do you get something reasonable if either one of the two components should always cancel it out? Why am I thinking wrongly here?
So this is a very good point, what you said about how we build now the total wave function. The total wave function is obviously, in this Born-Oppenheimer approach, a product of an electronic part and the nuclear part. So the thing that you said makes sense, but you don't have to worry about this product disappearing, because we're talking about different coordinates, right? We are talking about electronic positions and core positions, and of course it is not possible to have the electron located at the position of the atom, but you still get a meaningful result for each of them, and also the product of them creates a wave function that makes perfect sense. So because they are basically living in different degrees of freedom, you have electron coordinates and nuclear coordinates. But what you say is a good point. You pointed out that it is a product. And that's the idea. If you remove the coupling, if you remove these coupling coefficients, then the simplification is that we can say, okay, if it's decoupled, then my total wave function is simply a product of an electronic wave function and a nuclear wave function. And why did we do all the maths if we put this in the end to zero? We did it because this also allows us to go beyond Oppenheimer. And this goes as following. Look at my sketch again. I will stop sharing so that you can see better what I'm going to show you. So this is the typical situation where we said, okay, let's look at the ground state, at the electronic ground state. We can now solve the nuclear Schrödinger equation for our molecular system in the electronic ground state. I'll do this now by hand by estimating the lowest vibrational energy level of my molecule in this ground state. Will be somewhere here. I can also estimate how the wave function is going to look like. It will look like this. How do I know this? And I'm sure you can tell me. It will be something like this. Why do I know this?
Because I approximated via the harmonic oscillator.
Exactly. Yeah. I can approximate the vibrational energies, at least for the first few vibrational levels, through the harmonic oscillator. Simply because, if you do a series expansion of your potential term at an extremum of your energy surface, the first derivative is zero. So the leading contribution will be the quadratic contribution. So in good approximation for small changes away from the equilibrium distance, you have a harmonic potential. And so the quantum harmonic oscillator provides you with energy levels which are reasonable estimates of your actual vibrational energies. I'll plot a few more. In the meantime, you think about the following questions. Which special functions are the solutions of the quantum harmonic oscillator? Right, so these would be the states. They are typically equidistant in the harmonic potential. You can see we're not really harmonic at higher energies anymore, so we will have some deviations, and in the end you will have to solve this problem accurately through some numerical technique like finite differences or whatever to get the actual eigenfunctions here in this potential. But if it was a perfect quantum harmonic oscillator, which special functions would be the solution for this type of differential equation?
Does it contain the Hermite polynomial?
Yes. That's the correct answer, right? It's the Hermite polynomials. That would be the solution for the harmonic, quantum harmonic oscillator. And so this is an orthogonal set. I can show you the first few states. I mean, right, would go like this. If you take the square, you get the probability. And so you can see you can solve almost on paper through this estimate with a harmonic oscillator or with a simple 10-liner in MATLAB or Python. You can solve the Schrödinger equation for the nuclei if you know the electronic energy as a function of the distance, because this gives you this potential in which you solve for the vibrational states, right? The tricky part is to calculate the electronic energy, and this is something we will discuss soon. But so that's the first part here. And now we can also discuss the situation where the Born-Oppenheimer approximation is no longer valid.
Can I yet ask another question before we go on? When you said that we're talking of the Schrödinger equation for the nuclei, you said that the potential is brought about by the energies of the electrons. What about the potential that is brought about by the existence of other nuclei? Is this irrelevant, or why do you only consider the electrons?
Right. This is also a good question. If you so the energy that stems from the Coulomb interaction between the nuclei is obviously just a function of the nuclear coordinates, and when solving for the electronic energy, this is just a constant that you add to what you get, right? And in these potential curves that I'm showing here, I have already included this energy contribution that stems. This is the part of the potential of the Coulomb potential, which only depends on the internuclear distance or the positions of the nucleus. So this is already included and gives us only if included this type of potential energy. Okay, so this is already part of the potential expression that we have as V of R and uppercase R. But when solving the electronic energy, you don't need this contribution, because you just calculate the electronic energy for a given arrangement of your molecular system. And the energy contribution of the nuclei through their Coulomb interaction between themselves, which is repulsive because they are same charged as positive charged nuclei, this is just adding a constant, right? So for solving the electronic problem, it doesn't make sense. But in order to get to the potential energy surface, which shows a certain minimum at some point, you must include then also this term, which is obviously a function of the nuclear position, because the closer you bring them together, the two nuclei, the higher the energy will go because of this repulsion. But you can see that these two counteracting contributions, the Coulomb repulsion, when you bring them together, and the electron interaction eventually lead to some equilibrium. And typically, and this makes most sense from a very simple electrodynamics perspective, an electronic distribution with electrons being between the two nuclei is most likely the stable configuration, right? Because you're compensating the repulsion between the two nuclei through having the negative charge somewhere in between. And you can also derive from this that an excited state where electronic distribution might be more diffuse, that there is less shielding of the repulsion between the two nuclei, and therefore excited states tend to be states where the molecule is slightly more extended, for example, right? So there are some things that make sense. We're in this regime where classical thoughts and quantum mechanics mix, but both are still helpful to understand what's going on. But let me now come to this question: when does the Born-Oppenheimer approach break down? What could happen? I've shown you two electric states here, electronic states, the ground state and an excited state. And what I did in the ground state was I solved the nuclear Schrödinger equation in this potential. Can I do the same thing for the excited state? Yes, why not, right? In this picture, it's the same thing. I have a potential energy surface. This one is higher because it's an electronically excited state. It has a different curvature. Therefore, in this case, it's a bit wider. So I would assume that my splitting is less pronounced as it is in the ground state. But I can simply repeat in this potential my way of solving for the nuclear wave function, and I get the corresponding eigenfunctions, and I'm done. So this means for these two electronic states, the Born-Oppenheimer approach is working nicely. And my total wave function of the molecule is the electronic wave function that describes this potential, multiplied by the nuclear wave function that corresponds to some vibrational state in this potential. Okay? And now I give you an example of a state where we have a problem. Can you anticipate a position of an electronic state, of an excited state that might be an issue here? What can happen? Look at the distance of the electronic states. What could introduce a problem?
On the electronic states or the nuclear states, the distance?
The distance between the two electronic states, so the distance between the potential surfaces. Yes, I already read a very good suggestion. What if the electronic states overlap, right? If the potential energy surfaces are so close together, I'll show you. Let's assume we have another state. Yeah, wait. Let's assume we have a third state somewhere here. So I just gave the numbers. First we had 1, 2. 1 was the ground state, 2 is some excited state, and the third state is now a state that is also an excited state. It seems that its equilibrium is at larger distances, and the problem is its energy for excitation is in a regime which is in principle also reachable through vibrational excitations. Okay? So I show you now a vibrational state of this molecule that can no longer be described within the Born-Oppenheimer approach. Okay, it's the fat black line here. Let's assume this is a vibrational state in the potential 1. then you can see that the molecule, when being excited to this type of vibration, can think, well, actually I have enough energy to also swap from state 1 to electronic state 3 while vibrating, right? So in the course of extension, this molecule reaches a point where a different electronic state comes in and is energetically basically degenerate with my electronic ground state. And therefore, in this vibrational motion, the two electronic states are mixed. And we see that in this moment, it's no longer possible to speak of a potential energy surface that belongs to just one state. So our concept of a potential energy surface is actually linked to the Born-Oppenheimer approach. And in the moment where the Born-Oppenheimer approach collapses, we don't have a defined energy surface anymore because it's a mix of two electronic states now. Okay, so this is a breakdown of the Born-Oppenheimer approach. Here, at this point where the two surfaces cross, it's a singularity, basically, where you have a full breakdown of the Born-Oppenheimer approach, because the two electronic states for this internuclear position are same energy, fully degenerate, right? So we learned the following, and now I go back to my slides. We see that in a scenario where the energies are sufficiently far apart, we can simply solve this Schrödinger equation to get our vibrational energies. But if there are states close by, then our original ansatz, and for this I have to go back a couple of slides to the very beginning, this ansatz here gives us the answer. It says, in order to be accurate, I have to describe my total wave function that corresponds to the total molecule, including electrons and nuclei. I'll have a linear combination of, and the whole basis I have of electronic states, not just the ground state, but all possible excitations as well. Fortunately, it's not so common to have many states intersect each other. It's just a couple of states, but this means that instead of just having a simple product of an electronic wave function and a nuclear wave function, in certain cases we will need a linear combination of these products. Okay, in the one that I showed you on the paper, it would be a linear combination of two electronic states, each of them multiplied with a corresponding vibrational state in this potential. So you see, okay, well, the Born-Oppenheimer approach doesn't really work here anymore, but it's not so far off. It's not that we have a million states that are interacting here. It's maybe two, maybe three. There are situations where it can be four, but it's a useful concept and therefore a standard approach, because from Born-Oppenheimer, I can always go beyond Born-Oppenheimer in a reasonable way by looking at where does it break down, what are my electronic states that are mixing in, and then in this Born-Oppenheimer picture, just include them in this series expansion to have at least those states involved that are actually mixing here. And it's always just a couple of states. Okay, so that's the idea. You have to solve this monstrosity of a coupled set of equations for a core, for nuclear and electron positions, only for a few electronic states, typically. And this is a field of its own in theoretical molecular physics or computational chemistry, because typically these types of Born-Oppenheimer breakdowns that appear happen due to symmetry reasons in molecules that have a certain symmetry, which then breaks apart. And at the moment where the symmetry consists, two states are degenerate, but then you have a symmetry breakdown because you move one atom a little bit, and the two degenerate states split up into slightly different energies, for example, right? So this is a very common feature in many high symmetry molecules. And so there is a whole set of classifications on molecular point groups that identify certain symmetries in molecules, which show types of Born-Oppenheimer breakdown in some of the electronic states. Here on the slides, I have given you also some a criteria basically to see where is Born-Oppenheimer valid. You can say it is valid in situations where these coupling elements that mix different vibrational states in different potentials, note the indices, right? So we have different electronic states, a state N and the state M, and we have the corresponding vibrational states in these potentials. They are coupled through the coupling operator, and if this expectation value here for the coupling term is smaller than the actual energy difference between the two electronic states, then we are fine. But this is exactly the same as saying, okay, well, if my potential energy surfaces are sufficiently far apart in comparison to the energy I have at hand for vibrational excitation, I'm fine with just one potential energy surface and can solve for my nuclear wave function on just one potential energy surface. Okay, this is an important concept. This is why I'm spending a lot of time on just these few slides, because I don't want you to ever forget. This is a very important way or simplification that we make, but you should know where it ends and what it implies. Because the concept of the potential surface only makes sense within Born-Oppenheimer, but I can use this concept also to describe this situation of potential energy surfaces that are intersecting each other. I just have then to think about the possible coupling, and my nuclear wave function will be something that allows the molecule, so when the molecule is vibrating, to also change the electronic state. And so in some aspects, Professor Koch is studying these types of transitions between molecules where you excite them in some electronically excited state, and then you also have a certain vibrational excitation in a given state. And depending on this vibrational energy that you give the system, you might also allow it to show some sort of transfer into a different electronic state, because you have this coupling where Born-Oppenheimer does no longer hold. But if the electronic wave function has a different character through vibration, all of a sudden in this electronically different state, you might have different selection rules for optical transitions, for example, right? So in the moment where you do a vibrational excitation, you have this mixing, and the molecule has access to different ways of relaxation, for example. So this is an important feature, and is something studied in current research. This non-Born-Oppenheimer or Born-Oppenheimer breakdowns. You will also encounter this term of adiabatic and non-adiabatic couplings. Has to do with this Born-Oppenheimer approach, because adiabatic means that you have electronic states that can be looked at separately, and non-adiabatic means that you have a coupling between these two electronic states through vibration. It's one of these weird ways where a double negation is introduced, the non-adiabatic state. But if you think about what diabatic means, then adiabatic and then non-adiabatic, you get back to diabatic, right? So you have this mixing of two electronic states in the case of a non-adiabatic coupling. But I won't go into this at all any further. It's just something that you should know. And from now on, we can assume the Born-Oppenheimer approach to be valid and look at the actual electronic problem. Okay, so we continue. And on slide 88, I was speaking about consequences of having the Born-Oppenheimer approach valid. Well, now in the diatomic molecule, it was easy to solve the Schrödinger equation for the nuclei because it's a one-dimensional problem, right? It's just something that almost looks like a quantum harmonic one-dimensional oscillator. I can solve this easily and get my corresponding vibrational states. Since it's quantized, I have a vibrational quantum number, typically nu, and I can estimate it's maybe something like h bar times omega times 1/2 plus nu in brackets. So that would be the energies of the quantum harmonic oscillator. So it's linear in the quantum number nu. Now what's happening if I have a molecule that's more complicated and consists of several atoms? For example, the triatomic molecule, as it's shown here. Well, you simply have more degrees of freedom in terms of molecular vibration. How many? And here, simple idea, if I have n nuclei in three-dimensional space, then this means I have 3 times n degrees of freedom, right? But then I have to subtract, because for molecules, we said we don't care about two things, which things are not relevant for the energy of a molecule somewhere in space.
Translation as a whole.
Right, this gives the 3 directions x, y, z, or the coordinates of the center of mass. So this is not relevant for the actual energy of the molecule. And the other 3...
Rotational position in space.
Yes, right. So you can think of it as, for example, 3 angles that distinguish the local frame of reference of your molecule from the laboratory frame that you're using. And it doesn't make a difference for the molecular energy unless you introduce a field and you have a direction that defines or that makes it relevant, because then your orientation with respect to the field changes the energy, right? But if there's no field, there is no interaction, and in general, this rotation or the position, these two things are not relevant. So I'm subtracting them. This means I have 3n minus 6 degrees of freedom that remain. So this is the number of my vibrational degrees of freedom, 3n minus 6. My question for you is, what's the dimension of a potential energy surface of the very same molecule? How many degrees of freedom do I have?
I think 3, because you have 3 internuclear distances, which you are referring to.
Yeah, but that wouldn't be enough. It's no longer working if you have 4 atoms. You will see you have more degrees of freedom. But it's not a complicated question, because it's a little bit misleading. But think about it. I said you have 3n minus 6 vibrational degrees of freedom. So this means by a linear combination of all these possible vibrations, you reach any molecular geometry that this molecule can be in, right? So if I have 3n minus 6 degrees of freedom for vibration, the potential energy surface has how many dimensions?
Same amount?
Same amount, 3n minus 6. Yeah, it has 3n minus 6 because this is the dependence. Also, these are the the dependence. Of course, as a surface, it is in a 3n minus 6 plus 1 dimensional space where it resides, right? Because you're plotting the energy, but that shouldn't confuse you. The energy surface depends on 3n minus 6 coordinates. In the case of a diatomic molecule, we only have 1 degree of freedom. Therefore, our potential energy surface is just a curve. And I have to say, or just remind you of some feature. If you have a linear molecule, it's not 3n minus 6, but it's 3n minus 5, because you have 1 degree less for particles which you consider to be in a point shape, right? Because they don't have an extension in space if you think of them as a point, and so you have 1 degree less that is relevant or is realized. So 3n minus 5 in case of linear molecules and 3n minus 6 in general. Now here's a triatomic molecule. So this gives us 3n minus 6. 9 minus 6 gives us 3 vibrational degrees of freedom. And somebody said 3, I should have 3, which was correct for the triatomic molecule, but simply because I can describe any type of triangle through the length of the 3 sides, right? So this would be the internuclear distances. So in this case, it's really the distances in between that define the potential energy surface. But this is a special feature of this configuration. If you add another atom to the system, you have 4. 3 times 4 gives you 12, minus 6 leaves you already with 6 vibrational states. So you need more degrees of freedom to describe all types of arrangements that this system can be in. If you look at the triatomic, this obviously 3 points in space are always in a plane. So if you start with Cartesian coordinates, you would use them in a plane, meaning you have 6 coordinates. And if you look at the vibrational states in the 6 coordinates, this is just a transformation that leads from Cartesian into this set of so-called normal coordinates that are the coordinates that basically, let me see if this is on this slide here, I think. Yeah. So when looking at a more complicated molecule consisting of several atoms, you have a 3n minus 6 dimensional potential energy surface. But what you always can do is you can, at the equilibrium, you can approximate your actual potential energy surface through harmonic potential curvatures in all degrees of freedom. And if you do that, then your total nuclear wave function can be written in good approximation as a product of one-dimensional harmonic oscillators, one for each of these degrees of freedom. So what you do is you just do an expansion, a Taylor series expansion of your potential energy surface in a higher dimension. So you have this term for the second derivative is the matrix. If you think about differential and integral analysis, you heard about the Hessian matrix, which is the matrix regarding second derivatives with respect to changes in the coordinates. You diagonalize this matrix, and this gives you the so-called normal modes of the molecule. So you make a transformation into a basis where the Hessian is diagonal. The corresponding eigenvalues are the frequencies. This is basically the curvature of your one-dimensional harmonic oscillator, and the corresponding eigen vector is your nuclear wave function. Okay, so that is the idea that meaning I can describe a vibration of any sort of a molecule, either in Cartesian coordinates or through a combination of these normal modes. And if you do what I just said, you take the Hessian, you diagonalize it, you have these frequencies, you make a product ansatz, you say that the total nuclear wave function is a product of harmonic oscillators. The difference here is then that normal modes are motions where all of the atoms in the molecule are affected, and in an in-phase type motion. So due to the way of how you solve it through this diagonalization. So it's a delocalized kind of motion, and in linear combination. So if you have a motion in a molecule that is, for example, just some tiny change of a bond length, then if you look at it in a normal coordinate or normal mode picture, then this little motion of just one atom would be a linear combination of several of these diffuse normal modes in such a way that it describes the position of just one atom. But you see, so these pictures are equivalent, but typically, because in the terms of energy, it makes sense to stick to the normal modes, because here you have a clear description. You can say in a molecule at a certain temperature, I'll have a certain occupation of vibrational states. Well, which states are occupied? Let's see. These are the energies in this degree of freedom. These are the energies in this degree of freedom. Each of them has its own vibrational quantum number. So in the diatomic, we just had one nu because we had just 1 degree of freedom. In a system like the triatomic, we have 3 degrees of freedom for vibration, meaning we have 3 quantum numbers, and we just have to refer to this vibrational state somehow. We give them names. In the case of this triatomic molecule, it's a Qx, Qy, and Qs. You see, Qs is the mode where the thing is breathing as a whole, so all lengths get extended, and the others are interesting in the sense that they are actually reducing the symmetry of the molecule while vibrating. So if it's an equilateral triangle, gleichseitig, then the Qs will leave it this way, but the other two will break it. And you see, Qx is even still more symmetric than the Qy. So this is the, let me see, this is the Qx. It reduces the equilateral to an isosceles triangle. So it goes from gleichseitig to gleichschenkelig, right? So, but it's still a higher symmetry than, for example, this type of vibration, which turns it into an arbitrary triangle at some point. So these are the 3 possible modifications you can do to a triangle, and by linear combination of these 3, you can create any molecular geometry of a molecular system consisting of 3 atoms. Okay, and now I have to speed up a little bit, but this was the most important point. Okay, the rest here, I think I don't have to go too much into detail. This is more like activating your knowledge from school. This is what's shown here on the slide 89 is just some concept which I want you to think about in order to form a molecular bond in this picture of now having a potential energy surface, energy as a function of distance. The way I was plotting the potential and the way it's plotted here is in such that at infinite distance, the energy is 0, right? So I'm setting the potential in a way that at infinity it gets to 0, meaning that whenever an incoming particle has a positive energy, it won't be a state that is bound, right? Because it has still positive energy at infinite distance. It has too much kinetic energy. So when it comes in, it reaches the point of reflection and goes out the way it was, right? So in order to switch from these states that are unbound to states which are bound, you have heard about this in analytical mechanics and theoretical physics. You have this, you might remember the separatrix that where in phase space you go from one type of movement to a different one. Here, if the energy of the system is negative, meaning you have an energy that would be somewhere here, you're obviously in a regime where you're in a bound state, because you cannot escape. The second atom is then bound, and it can only perform a vibration, as we were just discussing. Now, it's obvious, though, that an incoming atom has always a positive energy, unless it is colliding with a third partner in this regime where it can drop down to a bound state. So in order to form a molecule, you need actually not just two, but you need three particles, because you have to get energy rid of and conservation of momentum as well. So you need a third particle to take away energy and momentum, so that the second of the three atoms gets in a state which is bound and forms the molecular bond with the other atom and creates a molecule. So that is molecular formation. And another thing that I might just touch here briefly is a link of our potential energy concept to chemistry. Because if you have a molecule A and you have a molecule B, and both molecules react to form a molecule C, because they are kind of forming new bonds, then you can also think of the same process I just described. A reacts with B to C, as molecule C is something else before, with two parts of it being a different place in space, and then reaching a geometry where it is now the product C, right? So the reaction from A to B, or A with B to C, is simply a sort of abstract motion on our potential energy surface of product C, okay? Because the fragments it consisted of before, A and B, are just very crazy geometry arrangements, where one part of the molecule is very far to the left and the other one is far to the right. So it's actually just one energy surface. And in order to describe chemistry, you want to know what's the energy difference of this state of the potential energy surface compared to this other state, like the state where A and B are separate to the state where A and B are together and formed C. If this energy difference is negative, so this state is more strongly bound, then you know this must be an exothermal reaction, because the energy has to be dissipated when going from here to here. So the absolute difference between energies on the potential surface will tell you about thermodynamics. And another thing you can derive from the potential energy surface is the actual willingness of a reaction to take place, because when you go from this state to this state, there might be a more or less pronounced barrier between these two states. Why? Because when fragment A meets fragment B, they are not just happy right away. They will have to change their own configuration a little bit in such a way that they can form the new bonds. Or in other words, when bonds are formed, others have to be broken. And so this leaves the molecule for a moment in a state where it's higher in energy than before and after. And the height of this barrier will determine how fast this reaction is going to happen. And so if you have a potential energy surface and the state here and the state here, and you look at the simplest path that connects a reactant state to a product state, you will follow the state and check what's the highest energy that I have to overcome. This is called the transition state. And the energy difference between the transition state and where you started from will tell you how likely this reaction is going to take place, or in other words, how often it's going to take place. If you have an ensemble of these two reactants, you want to know what's the speed of the reaction. This is something you can immediately derive from the barrier height. So this is why potential energy surfaces and the ability to calculate them is of such importance, not just in physics, in spectroscopy, but also in chemistry and all of the chemistry that forms life, right? Because what we have in our bodies, enzymes are catalysts that make it possible for reactions to happen at 37 degrees, which would take 1,000,000 years, to happen without this catalyst being present, because it's so unlikely for this reaction to take place, right? So there is something that finds a shortcut and reduces this barrier, changes the potential energy surface in a convenient way, so that so that this process can happen at a reasonable speed and at the temperature that we're providing as human beings. Okay, so this is something you can just read. It's a reminder of school chemistry, the metal bonds, ionic bond and covalent bond. Maybe one last word regarding this rather or slightly unusual type, the intermolecular bond. So when we're talking about molecular bonds or bonds between atoms and how they are formed, obviously these are processes where the electron density distribution is changed, and depending on the electron negativity of a certain atom, its ability to keep its electrons, there will be a process where you have, if this is like the same electronegativity, then they will typically form a covalent bond and meet in the middle, basically sharing some of the valence electrons. If one electronegativity is much higher than the other, then the one with the higher electronegativity will pull off this electron from the other, which is technically leading to a different type of material, because then you have an ion. One is deprived of an electron, the other one has an extra electron. So this introduces a different type of interaction, because it's almost a pure Coulomb type interaction, forming an ionic lattice and the salt type structures, right? And the last and a little bit more unusual way is this intermolecular bonding. So even molecules themselves, when they have formed themselves and they are all happy in the way of how they are arranged in terms of their electron distribution, might feel some interaction between them through remaining dipoles that can be found, so dipole-dipole interactions, or I'm sure you've heard about this London dispersion or van der Waals type interactions, because you have fluctuating electron density distributions which induce a dipole moment over time. There is a net force that remains, which leads to this attractive motion even between neutral fragments. So these are other intermolecular types of interactions which play a big role in the way of how matter, especially living matter, is structured. And with this, I come to the end. We start with the recap questions. If you have the time, if you don't have, it's fine. I will simply launch it for those who are still interested. Today's code is KLCCJ. 3 questions. The first one is, when does the Born-Oppenheimer approach break down? We have a couple of options. When electronic surfaces intersect each other, or when electrons are moving faster than the nuclei, or when the energy difference between vibrational levels becomes comparable to electronic excitation, or when all non-adiabatic coupling elements are 0. So these are the options here. Second question is, how many vibrational degrees of freedom does this molecule have? And the last question, why are transition states on the potential energy surface so important for chemistry? The TS, so the transition state, determines the thermodynamics of a reaction. B, it determines the kinetics of a reaction. C, relative energy differences between possible transition states determine the product distribution. I haven't talked about this, but maybe you can figure this out. Or the TS determines whether a reaction is endothermic or exothermic. let's see. I see the first question has been accessed by 15. So I'll probably wait till we have about the same number for questions 2 and 3. Okay, so I'll stop. Thank you for participating. And we come to the solutions, starting with the first question. And I'm happy to see that you guys got them. Yeah, it's basically flawless. It's just that some overlooked that 2 answers were correct here. The correct answers are when 2 electronic potential energy surfaces are intersecting each other. Then we have a clear singularity. We have a full degeneracy for a given nuclear position. But it's also true to say when the energy difference between vibrational levels becomes comparable to electronic excitation energies, right? So it's because then this also means the potential energy surfaces are close enough for this to happen, because a vibration is comparable to an electronic excitation at the same time. Okay, then second question, how many degrees of freedom? Here you just had to count, and most were counting like correctly. The correct answer is 30. Just have a few, that made a mistake when counting and doing this subtraction. So I think, it's 2 or 3. That should be fine. 30 is the correct answer. It is a molecule that is nonlinear, so it's 3n minus 6. And the last question, why are transition states so important? The correct answers are transition states are determining the kinetics of a reaction, not the thermodynamics, right? The kinetics, because the TS state is just telling us the energy of the barrier and not the absolute energy between them. There is sometimes a correlation between same types of reactions, that if the thermodynamic changes, if some same type of reaction is having a larger barrier, then typically also the energy difference is not so big. So there is a correlation, but in principle, they don't have to do anything with each other. If you want to know thermodynamics, you need the absolute differences. If you need the speed of the reaction, the only thing that matters is the barrier height. But there is another point that was correct, and 50% got it right, which is great. I didn't talk about it. Relative energy differences between possible TS structures also determine product distribution, because you might have a situation where reactants can choose different pathways. It's like you going over a mountain area, and you have several transition states which lead to different valleys and cities on the other side of the mountain ridge, right? So it depends on the actual energy that you need to overcome this barrier in comparison to the other barrier where most of the people will hike to, right? And for the chemistry here, this means that the transition states that are low in energy will lead to a preference for a certain product state. So it's also related to product distribution. Okay, and with this, I'm at the end. I'm stopping recording.